oxygen. This rocket couldn't even get off the ground if it wasn't for oxygen. The rocket is driven upwards by a burning mixture of fuel and oxygen. Without oxygen, the fuel wouldn't burn. But burning on this scale needs a lot of oxygen, more than a rocket can get directly from the air. And anyway, in outer space where this rocket's going, there isn't any air from which to get its much-needed oxygen. So the rocket has to carry its own oxygen supply, but not as a gas, as a liquid. If you cool oxygen gas down to a very low temperature, it turns into a liquid. In this form, oxygen really does help the way things burn, as we discovered with the help of a chemist in a university laboratory. You've probably seen how a cigarette burns in air, but let's see how it burns after it's soaked up liquid oxygen. This biscuit's also soaking up liquid oxygen. But don't worry about getting your biscuits too close to the fire. Biscuits don't burn very well in air because there's not a lot of oxygen there. Neither does this cotton wool. You can hardly even see the flames. But when you've been soaking another piece of cotton wool in liquid oxygen, you've got to be a bit more careful. But liquid oxygen isn't just found in a laboratory. It's the form in which oxygen is produced and transported on an industrial scale. Today, producing and transporting oxygen is big business. In this country alone, thousands of tons of liquid oxygen are produced every day. It's done by drawing in air from the surroundings. The air is cooled down to form liquid air, from which liquid oxygen is separated. Today, the separation of oxygen from the air is done on a huge scale. Surprising when you think that just over 200 years ago, the very existence of oxygen in any form was unknown. But perhaps it's not so surprising when you think about it. Oxygen gas is invisible. To find out how oxygen was discovered and who the discoverer was, we came to a famous meeting place for scientists, the Royal Society in London. The library holds all the important books ever written about science. It was in one of the older books, published in 1789 and called Traité élémentaire de chimie, that we discovered the first use of the word oxygen. It also contained details of an experiment which in its day started a mini scientific revolution. Let's repeat this famous experiment for ourselves. To do it, we built a modern version of the original apparatus. The experiment was designed to discover the effects of heating things in a fixed volume of air. Like the original experiment, the air is trapped inside a bell jar which is standing in a trough of water. At the start of the experiment, the water level is the same outside and inside the bell jar. The reading on the scale is 2000. The thing to be heated is mercury, a substance which has long fascinated scientists. Heated mercury doesn't burst into flame, but something does happen when it's heated in the presence of the air in the bell jar. That is, only if it's heated for several days. The mercury becomes covered in an orangey-red powder. And that isn't the only change. The water level in the bell jar rises. And that tells us that some of the air inside has been used up during the heating. Today we know it's the oxygen. But why has the oxygen been used up? To explain that and the formation of the red powder, a new theory was put forward. A theory which we still believe in today. When heated, the two separate substances, oxygen from the air and mercury, join together to make a new substance, mercury oxide. That's the red powder. But the story doesn't stop there. Mercury oxide is a rather unusual substance. If we increase the heat, the mercury oxide changes. It changes back into the separate mercury and oxygen again. So we get back the pure mercury and the oxygen as the water level in the bell jar returns to where it started from. Of course, we can't actually see the oxygen, but that seems to be the only explanation that makes sense. The experiment proved the air was made up of two parts. The water level rose as an active part joined up with the heated mercury, leaving an inactive part in the bell jar. The water level fell on further heating as the active part was released again. But what about the proportion of the two parts? Repeating the experiment showed that they were always the same, 1/5 active, 4/5 inactive. It was after this experiment the active part was named oxygen. But in fact, it had taken many years to reach this conclusion. Paris of the 1770s, home of Monsieur and Madame Lavoisier. It was Antoine Lavoisier who put forward the new theory about the heated mercury combining with the oxygen from the air. But before he could put up the new theory, Lavoisier had to knock down the old one. When Lavoisier started his work, it was believed that when things burnt, or sometimes when they were just heated, they gave off a mysterious substance called phlogiston. Although this mysterious substance couldn't be seen or collected, it was supposed that as things burned, phlogiston was given off. Lost into the air. Everybody believed that as things burned, they lost phlogiston. Everybody, that is, except Lavoisier. He was convinced that there was another explanation, and he did many experiments to get the proof he needed. Again, we're going to repeat the experiments using modern reconstructions. The experiment involves a fixed volume of air trapped in a bell jar, and also in the bell jar a substance called phosphorus. The phosphorus is heated, in this case electrically, until it burns. As the phosphorus burns, the water level in the bell jar rises. This was Lavoisier's first important observation. When phosphorus burns, some of the air disappears. His next step was to get a measure of how much of the air disappears. A modern way of doing that is to use a gas syringe. Again we're using phosphorus, but this time in a round-bottomed flask with 100 centimetre cubed of air, plus another 50 in the syringe. At first the syringe moves out. You might think this is phlogiston, but it's not. It's just the air expanding as it warms up. As the air cools, it contracts and the syringe moves back. Not to the original position, but to the 20 mark. 30 of the original 150 centimetre cubes of air have been used up. Lavoisier's next step was to find out where that air had gone, which he did by heating metals in air. We're using magnesium for our reconstruction. Ignoring the weight of the crucible, the weight of our piece of magnesium at the start was 0.24 grams. The lid limits the supply of air so that the magnesium won't flare up as it burns. But the lid doesn't cut out the air altogether. Some air does reach the magnesium, and part of it, the oxygen, joins up with the magnesium. The magnesium and oxygen join together to form an ash. The ash weighs 0.4 grams, more than the magnesium we started with, an increase in weight. Lavoisier's second important observation: when metals are heated or burned, they gain weight. Lavoisier got the same result when he tried an experiment on sulfur, which he wrote about in this note on the 1st of November, 1772.
About 8 days ago, I discovered that when sulfur burns, far from losing weight, rather it gains weight.
Later in the same note, he mentions metals.
This discovery, which I have established through experiments, which I regard as decisive, made me think that what can be observed in the combustion of sulfur and phosphorus could well take place for all bodies which acquire weight through combustion.
The last part of the note is also of interest.
As it is difficult not to reveal to one's friends in conversation something which would put them on the trail of the truth, I thought it best to deposit this in the hands of the Secretary of the Academy until such time as I made my experiments public.
Lavoisier was staking his claim to these discoveries, but for the time being, that was as far as he went. He didn't then know about oxygen itself. For that, our story moves elsewhere. This is Bowood House in Wiltshire, the home of the Earls of Shelbourne. This corner of what is now the library hasn't always looked like this. Back in the 1770s, it was a laboratory. Most notably, the laboratory of this man, Joseph Priestley, and it was Priestley who made the next important discoveries in the story. Once more, we've used the evidence of the original drawings and writings to reconstruct his experiments using modern apparatus. This particular experiment was just one of a series Priestley was doing to find out what happens to a variety of things when they're heated. In this case, he was heating mercury oxide. Now remember, although we've seen mercury oxide being heated before, for Priestley, this was a brand new experiment. He had no idea of how important it was going to be. Nobody else had ever heated mercury oxide before, nor had they collected the gas which was given off. In our reconstruction, we collected the gas in a syringe. The gas was then pushed out of the syringe and transferred to a boiling tube so that the gas could be tested. Priestley first used a glowing splint. It caught fire again when put in the gas. Next, he used a wax taper and noticed that it burned even brighter in the new gas. You can see the difference with a tube of ordinary air. The taper quickly goes out. Priestley did another type of experiment, not with burning things, but with breathing things, with mice. Priestley put 2 mice in the same sized bell jars, one filled with ordinary air and one filled with the new gas, oxygen. In that way, he could compare the effects. After a quarter of an hour, the mouse breathing air collapsed. He quickly took it out. It wasn't until half an hour that the mouse breathing the oxygen collapsed. That one too was removed. As far as breathing was concerned, oxygen was better than ordinary air. Priestley was so surprised with his discovery of the new gas he couldn't wait to tell people.
This experiment might have satisfied any moderate sceptic, but however, being at Paris in the October following, and knowing that there were several very eminent chemists in that place, I frequently mentioned my surprise at the kind of air which I had got from the preparation to Mr. Lavoisier.
And that was just the clue Lavoisier had been looking for. The gas was the missing link in his theory of burning. So we can say that it was not one person, but 2, Lavoisier and Priestley, who discovered oxygen. Or can we? Neither Priestley nor Lavoisier could have known that 2 years earlier, in a chemist's shop in Sweden, this man, Carl Wilhelm Scheele, had also been doing some interesting heating experiments. In his apparatus, any gas given off was bubbled through water contained at the bottom of a leather bag. Here's a reconstruction of one of his experiments. The substance that Scheele was heating was one that had been known for some years, a nitrate. What nobody seemed to have done before was to heat a nitrate. Scheele found that a gas was given off, a brown gas. He found it would dissolve in water, and that's why we're bubbling this gas through a bottle of water in our apparatus. The brown gas dissolves in the water, but there's also an invisible gas that doesn't dissolve, and we're collecting that in a syringe. Just a few minutes later, and the syringe is full. The gas is again transferred to a tube for testing. It relights a glowing splint. It's oxygen. So heating nitrates produces oxygen, and it was Scheele who was the first to make it, although he didn't know what it was. Then remember, it was discovered the same gas can be produced by heating mercury oxide, and it was Priestley who realized it was a special gas. Finally, it was discovered that this special gas is used up in burning. That discovery, together with naming the gas oxygen, was Lavoisier's great contribution. But even Lavoisier couldn't foretell the many modern uses of oxygen. It's vital to life. It helps breathing in an emergency. It enables you to go where there's no air. Oxygen improves burning. It makes flames hotter, hot enough to melt metal. And even hot enough to melt concrete. Although Scheele, Priestley and Lavoisier wouldn't recognize the production of oxygen today, they were the pioneers. It's their discoveries which eventually made all this possible.
Exploring Science ends daytime on 2 for this Tuesday.